Okay, just a little reminder of what we have done yesterday before I start. I just wanted to remind the definition of the Voronoi domain of positive definite quadratic forms, since it will be the main object of study today. So recall that for a given quadratic form A, with a set of minimal vectors S of A, so the set of integral vectors achieving the non-zero integral vectors achieving the minimal value of the form. To each of these minimal vectors, you associate a rank 1 symmetric matrix by this rule, and then you take the conic hull of all these rank 1 matrices as X runs through the set of minimal vectors, and what you get is what I called yesterday the Voronoi domain of A. And I had given some examples of Voronoi domain. So here is the Voronoi domain of a quadratic form with two minimal vectors, and then this is a Voronoi domain of a quadratic form with 1, 2, 3, 4, 5 minimal vectors. Okay, so I skip, so sorry for this. Okay, so what I want to explain today is the second part of Voronoi theory, that is how you get from these Voronoi domains of quadratic form GLN-Z invariant tiling of the cone of a positive definite form. So yesterday we explained the connection of perfect forms with sphere packings. So I won't go further on that direction today. And then we study the Voronoi domains for themselves. And what I will explain is the following. So I will explain how this Voronoi domain provide a tiling of the space of quadratic forms, meaning that every positive definite quadratic forms belongs to the Voronoi domain of a perfect form. Also, there are some very specific incident properties between the Voronoi domains of two quadratic forms, namely two Voronoi domains of distinct quadratic forms, perfect or not, intersect along a common face. And a very strong property, which is that essentially the Voronoi domains are disjoint. Well, not exactly, but the property, the important property is that whenever the Voronoi domain of a quadratic form A intersects the relative interior of the Voronoi domain of another quadratic form B non-trivially, then it means that the first Voronoi domain has to be contained in the second one. So I remind that by relative interior, I mean the interior, the topological interior, but inside the affine subspace generated by this convex hull, which is not necessarily of a full dimension. Okay, so this is a very strong property, which is important for cohomological application. And in particular, when you restrict this property to perfect forms, it means that, so I remind that perfect means exactly that the Voronoi domain has full dimension, or in other words, that the interior, the real interior, this time, the interior of this Voronoi domain is non-empty. So the one consequence of this property is that if A and B are non-proportional perfect forms, then the interiors of their Voronoi domains are disjoint. So this is a very important property. So I will give more details on that in the next slide. But already I want to mention that this tiling obtained by this Voronoi domain is finite up to GL and Z. So this is not difficult to prove, since we know, this is something I mentioned yesterday, that there are only finitely many perfect forms up to the action of GL and Z. And I didn't give a proof of that, but it's a rather easy fact using standard reduction theory. So since we know that there are only finitely many perfect forms, this immediately gives the finiteness of this tiling. Well, finiteness, I insist, is to be understood under the action of GL and Z. And moreover, and this is a really important fact, there is an effective procedure to compute representative of these perfect forms, and to compute the graph, the corresponding graph. So what is this graph? This is the graph consisting with vertices consisting on the perfect forms up to GL and Z. So the vertices of these graphs are the perfect forms up to integral equivalence. And the edges, this is what I will explain now. Two perfect forms define an edge in the graph. So in other words, we say that they are neighbor forms. If their Voronoi domain, which are of full dimension in this situation because they are perfect, their Voronoi domain share a common codimension 1 face. So I will give some illustration of that on the next slide. So my aim here is to explain in more detail how one builds this graph and the corresponding tiling. So I give a brief outline of the algorithm which produces this graph and this tiling. So to start with, you need to have a perfect form. So this is not completely obvious task. I will explain later how one can do that, but assume for a while that you are given an initial perfect form. You have one given by some process. And so you can consider its Voronoi domain, which I represented here. So you see it has codimension 1 faces, which I call facets. And the process of the algorithm consists in compute the so-called neighbors of this initial perfect form. So what does it mean? It means that for each of these facets, we will construct a new perfect form, the Voronoi domain of which will share the given facet. So for instance, here you see on this picture, I've represented a new Voronoi domain in green here, which shares a common facet here with the initial red Voronoi domain. Okay. So then you do that for each facet. So here you see, so here there is a new a first neighbor corresponding to this facet. Here another one. Here a third one, and there a fourth one. Okay. And then you continue with the newly constructed Voronoi domain. You apply the same process, which means that you will compute the neighbors, say, of this green Voronoi domains through the different facets, and the same with the blue one and the other ones, and so on and so forth. So I represented the previous situation viewed from above, which maybe is a little more easy to see. So you repeat the previous step with the newly constructed perfect forms until no new perfect form is found. So meaning that each time you compute, say, a neighbor, you compute the corresponding perfect form, and you test whether or not it is equivalent to one of the previously computed perfect form. And since you know that there are only finitely many perfect forms up to JLNZ equivalents, the process has to stop. Okay. And of course, in the previous step, you just disregard perfect forms which appear and would have already appeared in previous steps. Okay. Well, so this is the general principle of the algorithm. So now I will explain in little more details how you perform step 2, meaning how starting with a perfect form A0 and a facet of its Voronoi domain, how you compute a new perfect form, the Voronoi domain of which share a common facet with the initial one. So this is what I will explain now. So how does it work? So you start with your given perfect form. And as I already mentioned yesterday, to each facet you associate so-called facet vectors, which are by convention directed inwards towards the interior of the domain, just like this green arrow. And then if you look at the minimal vectors of A, so here the minimal vectors of A correspond to the different rays of the domain. And so you have the following alternative. Either the rank 1 form Q of X belongs to the facet, the codimension 1 face you are working with, which means exactly that the scalar product of Q of X, so I remind that Q of X is exactly this matrix. So the assumption that Q of X belongs to the facets means exactly that the scalar product of this matrix with the facet vector F is 0. And in this situation, it means that whatever T is, so whatever the value of the parameter T is, the form A plus TF. So if you move along the line starting from A and directed by this vector, then the value at X doesn't change because of this property. So in particular, since X was a minimal vector, this value still equals the minimum of A. On the other hand, if Q of X is not on these facets, it means that this scalar product is positive, and to the contrary, it means that the value of this form on this vector is strictly greater than the minimum of A. And so what does it mean? I remind you that yesterday I explained that locally, when you move around a given quadratic form, the set of minimal vectors can only shrink. You cannot gain new minimal vectors initially. So because of this property, you see that when you move along this line, as long as t is small enough, you will keep all the minimal vectors which belong to the facet corresponding to F, and lose all the others. That's what happens. Oh, I forgot to say and to write that here, contrarily to maybe what I said, t has to be positive, otherwise it doesn't work. So here I forgot to say that t is positive, otherwise it doesn't make sense. Sorry for that. The precision is given here. And so that's exactly what I have just said. So for small enough positive t, you have the property that the minimum of the form A plus TF remains the same. And the Voronoi domain of this form, since you have lost all the vectors, the minimal vectors, which are not coming from the face F, the Voronoi domain of the newly constructed form is exactly the intersection of the initial Voronoi domain with its face. So here on this picture, it corresponds to the blue triangle. Okay? Yeah.
Did you say what happens to vectors that are not minimal vectors?
They stay. I mean, because of the property that locally the minimum can only. So for small enough t, the vectors which were not minimal for A stay not minimal for this form. Because this means that, so for vectors which are not in the set of minimal vectors of A, this means that A of X is strictly greater than the minimum of A. And so for small enough positive t, it remains true for A plus TF. So for small enough t, of course, when t will grow, we will gain new minimal vectors. That's the point. But for small enough t, what happens is exactly this: you lose the minimal vectors which were not on this face set, and you don't gain any new minimal vectors, at least for small enough t. Okay? That's the general principle. So this is very, very simple. So all the question is how far can you go on this half line and keep this property? So what turns out is if you go far enough, then you will gain a new minimal vector. So that's the key, the clue of the algorithm. So to be more precise, so you keep moving along this half line until a new minimal vector appear. And to be precise, we define T sub F as the supremum of the the positive t such that the property here that the minimum of A plus TF does not increase is satisfied. So you define the supremum of this set. So of course, here I'm cheating a little bit because this supremum could well be infinite. A priori, there is no reason. I mean, this property could hold forever, whatever t. But in fact, it does not happen. So this is something I won't prove. It's not difficult, but I won't prove it. So this is the technical part of the proof. I prefer to skip it, but it's not easy to show that. It is easy to show that T of this supremum is actually finite, and moreover, it's a rational number. So just a word about the way one proves this. In fact, what one proves is that for big enough T, this form, if you choose, say, T very big, then this form will no longer be definite. This is something that one can prove. This is because the facet vectors are not, one can prove that the facet vectors are not definite. So for big enough T, so remember that A is a positive definite form, so you add something which is symmetric. And what I claim is that for big enough T, this will be degenerate. And this implies that somewhere in between, before losing definiteness, you will first gain a new minimal vector. Before the minimum decreases, there will be a new minimal vector which will show up. Okay. And for this particular value of t, what happened is that the newly constructed form is perfect. It has at least one new minimal vectors. Of course, on this picture, I represented only one new minimal vector, but it could well have several minimal vectors appearing simultaneously, but at least one new minimal vector shows up. And what is not difficult to see is that the Voronoi domain of the newly constructed form intersects the previous one along the facet F. So that's the general principle. So of course I've hidden some technicalities. I mentioned them, and in particular this property that this supremum is finite, which is crucial. Well, there are some extensions of this theory that I maybe will mention at the end of the talk, where this property no longer holds. So meaning that there are some variation on the Voronoi theory where for some facets you meet what one calls dead ends, meaning that you move along a given facet vector and you will never reach a new perfect form. So it can happen in some extension of the theory, but in the original Voronoi theory, in the setting of classical perfect forms, classical quadratic form, it never happens. Whatever the facet you choose, when you apply this process, you will finally reach a new perfect form. Okay. So this is, I think, the core of the algorithm. And so moreover, so one can prove also that this is a rational number, and there is a rather easy way to actually compute it. There is no mysterious stuff here. Okay. So let us summarize what we get from that. So if we elaborate on the previous ideas, what one can prove is that starting with the quadratic form, so this time with no assumption at all regarding perfectness. So I start with a random quadratic form, positive definite, I forgot to say. Then using the previous idea, one can construct a perfect form A such that Q is inside the Voronoi domain of A. The way to perform that is, well, maybe I don't give detail on that, but it's based on the same ideas I've just explained. You just move along suitably faced vector, and if you choose suitably your facet at each step, at the end you will necessarily end inside the Voronoi domain of a perfect form. That's something that one can show. And what does it mean? That means that the cone of positive definite form is contained in the union of the Voronoi domains of perfect forms. And as I already stated, this union is disjoint. Well, if you just keep non-pairwise inequivalent perfect forms, and up to GL and Z, this is a finite union. Yeah, there are. It's not a disjoint. You're right. It's a little abuse of notation. It's not a real disjoint union up to the codimension one facet in common. You're right. Okay. So moreover, if you choose two perfect quadratic forms, then still using the same ideas, you can construct explicitly a chain of perfect forms going from A to B with the condition that two consecutive perfect forms in the chain are neighbors, meaning that their Voronoi domains share a common facet, just as we explained before. Okay, so this is something you can prove easily with the tools I mentioned before. And so one remark, so remember that in the previous slide, I assumed that we were given an initial perfect form, and I mentioned that this in general is not so easy to find a perfect form, but in fact, one of the aftermaths of all this stuff is that if you don't have a perfect form at the you needn't worry about that, because you start with any quadratic form, and applying this process, namely the first step here, you will end up with a perfect form. So there is an explicit way to construct a perfect form starting with any positive definite quadratic form. So this is a remark I wanted to state. So far, I've only stated that we have this inclusion of the positive definite cone inside the union of the Voronoi domains of perfect forms. I want to be a little more precise. So first, So we have this inclusion. And on the other end, you remember the Voronoi domain of a given form is convex hull of rank 1 forms. So necessarily it is contained in the closure of the positive definite cone. Namely, all forms, all quadratic forms here are semi-definite positive. Okay, but we get something a little more precise, which is that what we tile exactly is not the closure, the whole set of semi-definite positive form, but only what is called in the literature the rational closure of Pn. That is to say, so this is a set of semi-definite positive forms, the kernel of which is defined over Q. And well, this is something you can prove a priori without using Voronoi theory. You can prove that well, at least you can prove one inclusion, but it's not so easy. And in fact, this again is something you can easily prove by using the idea that I have mentioned before. So I don't give details, but this precise description of the union of the Voronoi domains, and the fact that what you get is exactly this rational closure of Pn, which is not a triviality. This you can get explicitly by using the Voronoi algorithm. So this is something important, I think. Okay. So maybe in the, I don't know how much time I have. 25 minutes? I don't know, when do we start? Did we start? Okay, so maybe I was a little too fast, but it's not a problem. So I will just mention, maybe I will provide more details on this last part than I initially intended. So under the request of Philippe, I will explain how all this stuff can be extended to a wider context. Namely, so far we have spoken only of GLNZ, and although it's maybe a little hidden in what I've told, this Voronoi complex here provide a tool to compute the homology of GLNZ. So this part I won't explain. This will be, I think, mentioned in later talks this week. But it turns out that this general principle can be extended to a wider context, and in particular, you can similarly get a complex built in a similar way, which allow to compute the homology of other arithmetic groups related to number fields. So that's what I will explain. So to be more precise, all what I have described so far can be extended to arithmetic groups of the shape GLN of O, where O is maximal or not maximal order in a semi-simple algebra over Q. So I think this was initially noticed by Avner Ash in a paper or a series of papers in the 80s. So I will give some indication on how it works, but maybe only in one simple situation of, I won't take a random semi-simple algebra, but I will stick to number fields, which is a little easier to explain. But before speaking about number field, I just want to mention something we've done recently with Gabriel Nebe, Oliver Brown, and Sebastian Schönenbeck. We use that principle in some situation which can appear rather silly, namely when n equals 1. So when n equals 1 in terms of quadratic forms, you are quadratic forms with one variable, which can seem rather stupid, but it's not. And in particular, so I won't explain it today, but elaborating on the idea I've explained before, you can obtain an algorithm to compute, oh, there is a misprint, to compute the unit group of O. And what means to compute the unit group? This means that at the end you get a presentation of the group by generators, so finitely many generators and relations. So the way it works is you build the graph, the Voronoi graph of quadratic forms showing up in this context. And attached to each vertex, you get stabilizers. And using the Basser theory of graph of groups, you kind of, for free, obtain a description of your unit group. So, of course, the algorithm you get is not very efficient. So if you remember yesterday, I give some indication on the number of perfect forms you get in the classical context, and you saw that the number of perfect forms grows dramatically as the dimension grows, which means that the corresponding graph will become more and more complicated. So here the dimension is fixed and it's 1, but still the order and the underlying semi-simple algebra varies, and as the algebra varies, so to a given order is attached are attached some invariants. And it seems that one of these invariants, the discriminant, has an influence on the number of vertices you will find. So what we found experimentally, and we have no theoretical explanation for that, is that the number of vertices of the graph you get here in this process seems to grow together with the discriminant of the order. Okay, and so we have applied that to various algebras, quaternion order in quaternion algebras, and also in more sophisticated algebras. And we have performed a lot of computations that were new, in the sense that the algorithms in the literature did not allow for the computation of the unit group. So just, and I will stop with that topic, but for those who don't know this topic, one has to know that in general, this task of computing the unit group of an order in a semi-simple algebra is a difficult one. In the case of number fields, well, there is a structure theorem, the unit Dirichlet theorem, but besides that, as soon as you leave the world of fields, I mean algebraic number fields, the question of computing the unit group is a very difficult one. both from the theoretical and algorithmic side. Okay. So this is one example of what can do with Voronoi algorithm. So now I will describe what we can do in the more specific case where the order we are working with is ring of integers of a number field k. So in that case, you will see that the situation is really close to the situation over Z we have described so far. I just have, in fact, to define a set of notation and objects which will play the same role as the cone of positive definite quadratic forms in the classical theory. So I don't assume any knowledge in number theory, except the fact that given a number field, so a finite extension of Q, you have a well-defined signatures which count the number of real embeddings of K in R and the number of pairs of embeddings in C. This corresponds, of course, to the numbers of real, respectively complex roots of polynomial defining your extension. So this is classical. And in other words, this means that when you extend the scalar from Q to R, you have this isomorphism of algebras. And extending this principle to the set of symmetric matrices, what you obtain, I mean, the natural object to consider is this product of R copies of the space of n by n real symmetric matrices, so corresponding to the real embeddings of your field. And corresponding to the complex embedding, you have S copies of the Hermitian, of the space of Hermitian matrices over C. So this object here, in this situation, will play the same role as a set of n by n symmetric matrices in the case of in the classical Voronoi theory. So what is a typical element of this set? This is just R plus S tuple of forms. So the R first components are symmetric, real symmetric matrices, and the S last components, or there is a misprint here, the S last components are Hermitian matrices. So inside this space, you have a cone of positive definite forms, meaning that on each component you restrict to the set of positive definite forms here, positive definite symmetric form and positive Hermitian forms here. Okay. And why is this construction natural? Well, for instance, if K is totally real, meaning that the polynomial defining it as only real roots, then it's easy to see that this set is nothing else than the set of symmetric matrices with entries in K, for which you extend the scalar to R. And similarly for a CM field, which means a quadratic, a complex quadratic extension of a totally real number field, then this set can be viewed as the set of Hermitian matrices over K. So there is a well-defined complex conjugation on K in this case, and then you extend the scalar to R. So this remark is here just to say that this construction is natural. Okay? So what you do with that? Well, just as we have done before for quadratic forms, you define a scalar product on this space of tuples, which is nothing else than the scalar product we saw previously, but which you define component-wise in a sense. Well, there is a factor here corresponding to the fact that the complex embedding come in pairs. Well, this is a detail. And so we will need some rank 1 forms corresponding to minimal vectors with which we will build Voronoi domains. So how it works? So starting with the column vectors with entries in K, if we denote by xi its image under the ES embedding of K to the n into C to the n, so corresponding to the embedding of K in C that you extend to K to the n. So for each embedding, you get a vector in C to the n, or in R to the n if the corresponding embedding is real. And so with that, you build a tuple, the component of which are of this shape. So quite similar to what we have seen in the classical setting, except that you have to add complex conjugation in the Hermitian case. So the complex conjugation is just the identity at real components. Okay, so this is quite natural. And again, what will be important is this property. And so we will define the evaluation of a tuple A in SNK K at a given vector. We will define this quantity in such a way that this property holds, because we want this property. We want that the evaluation of a form in this set on a vector x can be interpreted as a scalar product of your form against one of the rays of the Voronoi domain. So the way to achieve that is to define the evaluation of A in this way. Okay, so this is perfectly natural. And then once you have defined all that stuff, you have to believe me that everything I've explained before works again in this setting, meaning that you can define Voronoi domains. You can define the minimum of a form with respect to this evaluation. You can define minimal vectors. You can define Voronoi domains. These Voronoi domains have the same nice properties as in the usual case. And they provide the tiling of your space. So namely, if you define the Voronoi domain of such a form, so this still is a polyhedral cone inside this real vector space. Again, you define perfection by the property that this polyhedral cone has a non-empty interior. And then again, you have a neighboring graph, the same process I've explained before. You have an algorithm to compute the graph. You have finiteness with double S, sorry for this misprint, up to GLN OK equivalence. Everything behaves nicely. And finally, you get, as in the usual situation, a tiling of the cone of the cone of positive definite form by the Voronoi domains of the perfect forms. And again, what you tile exactly is not the whole closure of the cone of positive definite form, but the rational closure, which is defined exactly in the same way as I did over Q. This is the set of semi-definite forms, the kernel of which is defined over the ground field K. Okay. And the proofs are quite similar. So just if I still have a few minutes, I want to go back to the previous slide to say a word about this formula. So the way we evaluate forms at a given vectors in this setting. So as I mentioned, and I stressed on this point, we choose this definition because it has this property, which is crucial in order that you get an algorithm and a tiling by Voronoi domain. But this property has some, this definition, sorry, has some drawbacks and is not very natural in many respects. And for instance, so you remember that in the classical case, say of a quadratic form over Z, when you evaluate a form at a vector x or at minus x, of course, you get the same value. And in this setting, you would like to have the same property. But what would play the role of +1 and -1 in this setting? The object to consider would precisely be the unit group. And the drawback of this definition is that it's not consistent with the action of the units, which means that the action of the units completely disappear in this story. So you get a tiling that you can use to compute, say, the homology of GLN. Okay, but you completely lose the action of the units. So in this respect, the situation is much less satisfying than in the classical case over Z. So there is a way to avoid that, which is here, instead of taking sums here, you replace these sums, including this one, by a product, and this 2 times by an exponent 2. So this can be thought as a trace, and what I claim is that one better take a norm instead of a trace. And then if you take the norm instead of the trace, then you keep track of the action of the unit, but you lose this property, and you can no longer apply the Voronoi process. So you have lost the most important part, which is this timing. Okay, and to finish with, I just want to mention a few references. So of course, the original papers by Voronoi, and also if you are interested in getting some detail, including details on the implementation of the Voronoi algorithm, I strongly advise you to have a look at this paper by Jürgen Obgenors, who explain in full details the Voronoi algorithm in a much wider context than what I did yesterday. So this is based on previous work by Kuscher in the 60s. So Obgenors extended it to the setting of what he calls dual cones. And he mentions several other applications of the Voronoi algorithm. For instance, he uses these ideas to compute the automorphism groups, some automorphism group of hyperbolic forms. So it's a very interesting paper, not so well known. So I take every occasion to make some advertisement on this paper, which, according to me, is the best reference on the Voronoi algorithm. So if you are looking for the definitive reference of Voronoi algorithm, you no longer have to look for it. It's here. Okay, and also, I don't want to forget to mention another reference on the topic, which is a book by Jacques Martinet. Okay, thank you for your attention.